This lecture will take what we've done with single degree of freedom, steady state response, and show how we can extend that to multi-degree of freedom systems. We'll see that it's all fairly simple mathematically if we just pay attention to a little linear algebra. Although if we decompose things a little more, looking at the modes of vibration, we can get a better insight into what's going on. So just a little bit of recap from last time. If we had a forced system, and we were interested in steady state response, so say we had a harmonic force, F naught cosine omega t. We talked through the fact last time that if we apply a harmonic force to the system, that the response will be at the exact same frequency or have the exact same period. And the two questions were just, what is the amplitude of response and what is the phase of the response? The amplitude and phase could both be shifted, but the response would have the same frequency. So that was for a 1 degree of freedom system. What happens if we go to 2 degrees of freedom? Well, we can do the exact same analysis, and it's so easy. I'll do it right here in just a couple of lines. So whereas before we assumed that the scalar x was equal to some real part of some scalar amplitude, e to the I omega t. Now we're going to assume that the amplitude is a vector. So let x be an n by 1 vector of complex amplitudes. So basically we're assuming that if the force is a vector f e to the I omega t, the response will be at the same frequency. Notice that this part here is scalar, so all of the degrees of freedom are moving with the same frequency. The forcing is at the same frequency. So all of those everything's at the same frequency. The only thing that can change is the amplitude and phase. And what do we mean by a force vector like that? A couple examples. One simple example is, suppose we have an airplane. One way we could get this is if we had two forces. Say over here we pushed with 10 newtons times cosine omega t. And over here we could also push with 10 newtons cosine omega t. And that would want to excite the first bending mode of an airplane. So, and this is actually frequently done in ground vibration test of airplane. The other thing that you might do is apply the two out of phase, so you could excite a different mode. And so, in this case, we have, here we had 10 and 10. Here we might have 10 and minus 10 cosine omega t. So those are two examples. So we can have a periodic force. We're just assuming that any forces applied, they're all at the same frequency. And we'll learn later how we could relax that if we needed to. And if that's the case, we're going to assume that the response will be at that same frequency, just that every degree of freedom might have a little bit different complex amplitude. All right, so we can plug this into that equation. Skipping just a step or two, what we would get is the real part of the mass matrix. Actually, let me first write the minus omega squared. Take two derivatives, that'll give us a minus omega squared. Real part of the mass matrix, x. I'll pull all the e to the I omega t's to the end. One derivative of this will pull down the I omega, so we'll get I omega c. Again, the complex amplitude x, e to the I omega t. And then we'll have k times complex amplitude x. Okay, and then all of that minus f. And then all of that e to the I omega t equal to 0. So everything in the parentheses here is just a number, a matrix, or actually a vector, an n by 1 vector of complex amplitudes. And the only way that this equation can be satisfied for all time is if every single one of those is equal. And so the inner part has to be equal to 0, and we can actually solve this for x. X would be equal to this inner part here. Let's try one more time. This inner part here. Okay, so it's all of this. Factor out the x's. All of this. And then we'll take the inverse times f. So there's a nice simple equation for the complex amplitudes x, right? And to get that, all we had to do was just a little bit of linear algebra. We just had to respect the order of multiplication. And so given the complex amplitudes of the force, we can get the complex amplitudes of the response. So what does this equation mean? Just to emphasize again, say instead of an airplane we had a bridge. It means if we apply a force somewhere on that bridge, at any point on the bridge, the response will have some complex amplitude, e to the I omega t. So it's going to be harmonic, right? And if we go to some other place on the bridge, we can have a different response. The only thing that can differ, though, is the magnitude and phase. So where that one looked kind of like a sine, here we could have a really, the frequency would have to be the same. Here we could have a really high amplitude cosine, for example. But they all have to be at frequency omega. So this approach, this direct approach, and again, this is in chapter 5 of Ginsberg. This direct approach is the fastest, the easiest. So if you're doing computations, there's a good chance you're going to do things this way. So this is an easy way to solve. The one thing this doesn't really do for us is doesn't give us a lot of insight as to what's going to happen. You know, what frequencies will cause this bridge to have really large amplitude vibration? How could we know that? How can we anticipate that? And so if we want a little more insight, what we'll do is we'll think about solving this in the modal domain. And just as a recap, we find the modes of vibration, the mode shapes phi and the natural frequencies omega by solving this eigenvalue problem here. An n degree of freedom system will have n natural frequencies, and it will have this mode shape matrix or eigenvector matrix. And we also have these orthogonality properties that phi transpose k phi is a diagonal matrix of natural frequencies squared. Phi transpose m phi is identity. All right, and we've already learned that if we plug this into our equation of motion, that what we'll get is uncoupled equations for j equals 1 up to n for each of the modes. So if we wanted to deal with the steady state response, we could plug in for the force our harmonic forcing. And then we notice that this product here is a 1 by n. It's an n by 1 transposed times an n by 1. So this is just a scalar. Or in other words, this product of the mode shape and the forcing vector is just a scalar. And it tells us how much is mode J excited. How much does that force affect mode J. And we could really spend a lot of time talking about that and thinking about that. I won't say any more about it right now, but there are a lot of really interesting things that happen. For example, say we had a mode 1-1, kind of like that symmetric mode of the airplane up there. And say our forcing was 1-1. This is supposed to be a transpose here. So the product of those two would be 0. So that symmetric forcing wouldn't excite that mode at all. But if we had the 1-1 mode, we'd get a forcing of 2, right? So that explains why when people do a ground vibration test, they might phase the forces in these particular ways to try to put a lot of force into one mode and to not put any force into another mode, so they can pick individual modes out of the response. But anyway, so that's a constant that tells us how much each mode is excited. And now this is just a 1 degree of freedom system. So this is exactly like what we solved before. We make the same assumption we made before, that now the modal amplitude has some complex, the modal response has some complex amplitude in J, e to the I omega t. And we just plug in, do algebra, kind of like the linear algebra we did up above, and we get this expression. So this is the amplitude of mode J, and in steady state still, right? And so it's a complex number that tells us how much mode J is excited. So, so that's really easy, right? And we would repeat this for all of the modes, and then we could collect all of those a to j of t's into a vector and plug back in using this equation. Plug back in, and we can find the response of the structure using that equation. I want to point out, though, one thing that's kind of cool about this equation is you see how I've written it in partitions like this. And if we size the partitions appropriately, we can actually rewrite this expression as phi1, real part of n1 e to the I omega 1t, right? And we just kind of follow the usual vector multiplication. So this multiplies that, that multiplies that, right? So we just get a summation of terms. Oh, sorry, this shouldn't be omega 1. This is just the omega. This is the forcing frequency. All right. So anyway, so that's a summation of terms. As far as the x's are concerned, this summation of terms will just give us some complex numbers, x1, x2. And so we can write x of t in the exact same form we assumed up above. This is just a process of finding the complex amplitude of the individual x's. But this fact here lets us write the x's, the amplitude of each of the coordinates, as this summation of terms. And basically this is that modal force that we talked about. And then this projects the modal coordinate back onto the physical coordinates here, right? So these are the mode, this comes from the mode shape matrix multiplication there. And then we sum that up over all of the modes. And this equation gives us a tremendous amount of insight into what happens in the forced response of multi-degree of freedom systems. And we'll see this so much and we'll use this so much that we'll give it a special name. We'll call this the frequency response function, or FRF matrix. And we'll write it this way, h of omega times the forcing. So the frequency response function matrix is just the h of omega part. Okay, so to help us understand what this means, I think an example will really help. So let's go back to our favorite 2-degree of freedom system where we have 3 equal springs, 2 equal masses. We're potentially forcing on each of the degrees of freedom. We could have a different amplitude and a different phase for each degree of freedom, but they're all being forced at the same frequency. And these are the equations of motion. Here I used m and k being 1/2 because it gives me this really nice mass normalized mass matrix. And but the natural frequencies are still what we found when we saw this example before, 1 and square root of 3. Okay, so we plug all of this in, and what will we get? Well, just schematically, this equation up here is going to tell us this equation is going to tell us the complex amplitude of each of the modes. Oops, that just made a mess. Let's see if I can clean that up without too much trouble. Sorry. If Microsoft will let me. Alright, sorry about that. Sorry, there's a little X hiding in there. Just erase that real quick. Just repair this here. Alright, and this was X1. Okay, anyway, so that equation tells us that the response of mode 1 will just have the modal force in it, and it has this denominator. And so notice when omega is equal to omega 1, these two terms will cancel, and we're left with only a small number. Oh, this should have omega 1. We're left with I omega squared, I omega 1 squared, 2 times the damping ratio. And remember, this is usually something small, like 0.01. So here there's going to be like a factor of 50x amplification, because 2 times 0.01 in the denominator. Right? And that's going to happen when omega is equal to the first natural frequency. And similarly, if we looked at that same equation for mode 2, we'll see the same kind of thing, only this time the amplification happens when omega is equal to the second natural frequency. And so we get these two responses. Away from the resonance, we get relatively small response, but at the resonance, we can get really big amplification, big response. And so the individual modes each behave like 1 degree of freedom systems. If we know the resonance, we know what frequency to avoid. Now look what happens though when we put that back together. We're going to multiply each of those quantities by the mode shape. So, so say we take this and we multiply here by 1, 1, by the first mode, right? And this will get us into physical coordinates. And when we do that, then we're going to get this same peak here repeated 2 times, each multiplied by 1. So now if we back out and we look at what happens to the individual masses, x1 and x2, we get this same peak showing up and we've multiplied by 1 here and 1 here due to the first mode shape. And so both masses, 1 and 2, show a big response if we excite near the first resonance. And similarly, if we did the same thing with mode 2, this one we're going to multiply by 1 minus 1, because that's the second column of that mode shape matrix. Here we'll have 1 minus 1. And because these plots are usually the magnitude, the minus 1 doesn't really matter. So this 1 minus 1, we'll see a peak there at that frequency as well. The only difference is when we're near that peak, these will be 180 degrees out of phase. So this tells us something really important about what the response will look like near each of the modes. Right? If we're near this first mode, the response will look like 1, 1 times real part of N1 e to the I omega t. Right? And so one of the ones is on mass 1, one of those is on mass 2. So we'll get the big amplification of that resonance, right? And the similar kind of thing happening at mode 2. So let's just show mathematically how that can work. So the response x, remember it's a summation of these terms. If we write that out for a 2 degree of freedom system, we get this. And if we're saying near omega equals omega 1, these two terms cancel. These terms don't cancel. So in this first term, we're going to have the quotient so we'll have that numerator over something small, right? Like 0.02 times omega 1 squared. For this second term, though, these two don't really cancel, and so we'll have some bigger number, say in this case this would be, we'd have this would be square root of 3 squared, or 3 minus 1, right? Plus I times this frequency. I'll just write that omega 1, omega 2, let's say zeta 2 was also 0.01, right? So notice this term is small, but this term is still pretty big. So this mode doesn't have much response near the first natural frequency. So we can pretty much just neglect this term. And we can say that the response is almost entirely mode 1. It's almost like we have a 1 degree of freedom system. And we'll use this fact in experiments, because if we want to know what the first mode vector is, and say we can measure x1, x2, well, near omega equals omega 1, the mode vector is this times some constant. And the constant's actually a large number that causes this to dominate. So we can get an estimate for the mode shape by taking the response, complex amplitude and phase, at a given frequency. So this is the foundation of experimental modal analysis, and something that we're going to use a lot in this class. It also just is the key to understanding what happens with multi-degree of freedom systems. If we force near any of the resonances of a multi-degree of freedom system, we can get a large amplitude response at every coordinate on the structure. And so this is an important thing to be aware of and to use. Okay, we'll talk a little more about that next time, but I think that's a good enough introduction for today. We'll see you at the next lecture.